So now this circuit is pretty close to identical of the last circuit except for a couple of things. The last video we had a 5.6 volt zener diode. This is a 5.1 volt zener diode. I grabbed this from the Joe Knows Electronics semiconductor kit. It does not have the 5.6 volt zener diode. And so if that was the only kit I had zener diodes for, I wouldn't have the 5.6 volt zener diode. So we have here a forward bias because you get that zener voltage while it's reverse bias. But with the regular rectifier diode, so I'm using the 1N 4001. It doesn't really matter what type you use, but this one you can tell. I have other diodes that look like that one. So there you can tell that's a rectifier diode. But in case we have that forward bias, so it's also going to build up about 0.6 volts. So together it'll build up about 5.7 volts. I needed to use a lower value resistor too. This is a 2200 ohm resistor to get the current through. I think because at very low current, the voltage drop isn't near is 0.6 volts there. So I had to raise the current a little bit. Looks like we're getting close to 5.7 volts even when we get down to 7 at the supply, and we lose 0.6 so that we get 5 volts out there, and that powers the load. Again, we have this emitter resistor that helps the emitter see where 0 volt is, 0 volt ground, in case the load throws it off for some reason. And we zoom back. So this is an auto range emitter. All I have to do is set it to voltage. If it has numbers next to it, set it to a number higher than what you're going to measure. But this is auto ranging. We have the voltage there. The power supply is down to our minimum right there, 7 volts. And you can see how much current approximately is flowing through the whole circuit. That current is not as accurate as a multimeter. But we can look at the supply voltage. It'll be a spec short due to resistance and stuff in the wires. Dropping a little bit of the voltage, and there you can see we got about 4.8 coming out. So this isn't a precision circuit. We're not going to get exactly 5 volts unless we're lucky coming out, but there you can see it's about 0.6 volts higher approximately. Again, it's not exact. And we can look at the voltage across. I could have left that at ground, doesn't matter. Negative supplies are connected together. Now we're going to come to the more positive side of the zener. And it's a 5.1 volt zener. You can see at this lower current, it's a little bit lower right there. And then we have the rectifier diode, just a regular silicon rectifier diode. And you can see it's about 0.6 at this current there. And then they add up, of course, that you can stack semiconductor voltages. So let's pop over. And 17 should be safe, but I think that 15 is probably about the limit that we should have. And we're going to get more current than we did in the last video because I got that lower resistor there. It's going to let a lot more current through than the 10K resistor we're using in the last video. So again, 15 volts. Main thing is the way we have this circuit wired up, we got 5 volts out, and now it's a little bit higher, but we got higher current going here. We're going to get a bigger voltage drop or bigger voltage buildup, I should say in this case. And there you can see higher base voltage. That's holding steady. This one's going up over time. Maybe it's getting close to leveling off. But like I said in the last video, when these bipolar junction transistors heat up, they start conducting better actually. So you have a problem where they're the ones limiting the current and they're heating up. They might just start conducting current better and it may be too much. So we saw a little more than 5 volts there. And a little more than 0.6 volts right there. Probably a bit higher, but they added up to probably a total voltage there of higher. So I wasn't paying a ton of attention to those numbers, but that's what you should have seen. So like I said before, the transistor starts conducting better when it's hot. Maybe we'll have a problem with thermal runaway. If it really ran away fully, then we would basically have the full 15 volts across that load, which would be too much for that LED. So we want to avoid thermal runaway. Let's make sure we turn off the multimeter. And now we will zoom in, take a closer look. Hopefully you can see that. We have the zener diode right there, 5.1 volt zener diode, and cathode goes to the more positive side, anode to the more negative side. Of course, that's the direction it's harder for it to conduct. Whereas the rectifier diode that we have here is forward bias. So the cathode, the gray band, is more negative. Anode is towards the more positive side right there. That's the direction that it conducts more easily. This one you would not raise the voltage. It's 50 volts for this particular one, so that it would conduct reverse bias. You only let it conduct while forward bias. That's the way it is with diodes, unless they're specially made like the zener diode. But in case we set that voltage to the base middle pin right there, because we are using the 2N3904 bipolar junction transistor. And I didn't show the pin layout on the diagram right there. We got the flat side to the right. So up there we got the collector. In the middle we have the base, and down there we got the emitter. Long lead, the anode of the LED. On top, short lead, the cathode. Again, it's also a diode. This one will definitely fry, based on my testing, as soon as it passes any current reverse bias. It just won't conduct anymore in either direction. It burns out. So long lead anode more positive, short lead cathode more negative. It will most definitely probably fry at 15 volts, but not at 5 volts if you put it backwards. I think somewhere between like 9 and 12 volts. These stopped working when I tested them. And there's our extra resistor going to ground just to help see that voltage. Probably don't need it in this circuit at all, but a lot of times, especially when you are dropping voltage like the LED does, it may not sense where 0 volts is anymore in relationship to the base voltage. So we got that. I put this 2K2 there. You may see that instead of 2.2K. Because a lot of schematic diagrams were handwritten or something back in the day, and people didn't see the decimal point. So what they did was they replaced the K in this case for kiloohms. They use that to replace the decimal point. So that's basically saying 2.2K. Hopefully that makes sense. We went up to 15 volts. I think that's perfectly fine, even though I used the example that if we had thermal runaway, it might put a full 15 volts across the load, which would be a ton of current as far as an LED is concerned. Probably wouldn't burn out instantly. It would get like very bright. The resistor might overheat. Worst case scenario, it catches fire or something. LED might burn out. But in case, you don't want 15 volts across this load right here. So you don't want to use enough voltage where this is going to heat up until you got thermal runaway. Looks like that's everything. So thanks for watching.